the last lecture, we discussed some special property related to the compactness. So that is finite intersection property. So it says that whenever we have a collection of open sets, which is not necessarily the collection of all open subsets of X, but we will choose a sub collection of open subsets of X, which is given, and we find the corresponding collection of closed subsets by taking complement of each element of A. Then we get family C, and A covers X if and only if the family C, the intersection of all elements of family C is null set. So this condition is known as C has empty intersection, or total intersection of C is fine. And in particular, if you take only finitely many subsets of elements of C whose intersection is phi always, then such a collection C is known as known to satisfy finite intersection property. So here in this definition, we are not taking elements of C are closed set. It may be any sets, right? So whatever family of collection of subsets of X, C is given, it satisfies finite intersection property if whenever we take n elements of that set, its intersection is always non-empty set. And then we discuss a result that a topological space X is compact if and only if for each collection C of closed subsets of X having. So whenever we take a collection of closed subsets of X, in which whenever it satisfies finite intersection property, that means whatever finitely many sets of C I take, its intersection is always non-empty. Then it satisfies this property that the total intersection is non-empty. Right. So this condition is equivalent to the compactness. So let us take some example to understand all these definitions. So if we take X to be R, so R with the standard topology. And then we consider this particular collection A of open subsets of X, right? So I am not taking all open subsets. I am taking a specific open subsets of R, which are n to infinity, where n is a natural number. Right. So for example, if I take n equal to 1, it is the infinite interval 1 to infinity. If I take n equal to 2, it is interval 2 to infinity, and so on. So we can easily see that this is a collection of open subsets. So the elements of A are open sets, and A covers X, that is R. So clearly, when I take union of each elements of A, so that means n, the set n to infinity, where n belongs to n. So n belongs to n means n running from 1 to infinity. So when I take union of each elements of A, then I will get entire space X, that is R. So this is very easy to see, because whenever I take any element X of the real line, whether it is positive or negative, I can always find a natural number n which is smaller than that, right? So in fact, I should take here Z, because there will be negative numbers also, right? So n belongs to z we need to take. So now it will be from minus infinity to infinity. So whenever I take any real number x, I can always find uh, an integer n which is smaller than x. So therefore x belongs to n to infinity for some integer n. Right. So we can also choose n by taking integral part of x. That is also one way to choose n. So therefore this is basically the proof of this fact that every uh, this union covers entire R. So therefore what we have proved just now is that A covers X. Right. So A is some subsets, some uh, collection of open subsets of X which covers X. Now what is this corresponding collection of its complement sets? So let's see be the collection of all complements of elements of A. So that means it is X minus that set. So X is R, that means it is R minus n to infinity n belongs to Z. Right. So now what will be this set? If I take complement of the infinite interval into infinity, then this set will,
minus infinity
yes, minus infinity to
to that to n
close n.
closed.
Right. Very good. So this will be the basically closed interval, right? So all these elements are closed subsets.
So actually, I have one doubt. That
Yes,
you have defined that union it covers a
yes,
it's starting from minus infinity.
yes.
So is this well defined
Which you
this
are saying?
union
This one.
that union? Yes sir, yes sir.
Yeah, this is well defined because basically what are these? Uh, okay, so you are saying that the n is minus
No, sir,
infinity to
it can be
infinity.
represented into
Yeah. Right.
into two
So
unions and
no, no.
equals minus into of integers.
See, what do I mean here exactly? What you are saying is right. So I should write n belongs to z.
Yes sir, yes.
So now I think it is there is no confusion. So you are right. We cannot write like series. We should write in this way. N belongs to z. Okay, fine. So now the question is that these are the C is collection of corresponding collection of closed subsets corresponding to the given family A. So now what is the we want to check whether the total intersection of C is null set or not. So that means we need to check n belongs to Z, the interval minus infinity to n. What will be this? So what will be this set is however it is clear, but still we can observe by real line. So whenever I take the interval 1 to minus infinity to 1, that will be this set. Then I will consider the second interval, that is minus infinity to 2, same way minus infinity to 0, minus infinity to minus 1, minus infinity to 3. So all these sets are all contains all these elements. So for example, if I take minus infinity to 2 intersection minus infinity to 3, what I will get is minus infinity to 2, right? So now whenever I take the total intersection, so basically I am getting the smallest interval, and all this interval will is the decreasing sequence of intervals because minus infinity to n uh, always contains minus infinity to n plus 1, right? So using this, we can observe that the intersection is null set. Right. So this is what I have mentioned in the last lecture, that whenever we take the intersection of all the elements of C, we get the null set. So that means the total intersection of the corresponding family is null set, and then it will come this particular notion will come. So let us take one corresponding example, that so is the family C defined by minus infinity to n, n belongs to C. So that is what we considered here. So is the family of subsets of R satisfy finite intersection property. So answer is yes, and the proof we have already discussed somehow, that whenever I take any two elements of particularly this set, then it will be of the form minus infinity to n1 and uh, minus infinity to n2, right? Any two elements. So that means what? That means n1 and 2 are integers, right? So when since n1 and 2 are integers, we can always find what is maximum, what is minimum. So let n2 be the minimum of n1 and n2, right? So it is also an integer. So question is that what is finite intersection property? Whenever I take a finite subcollection of elements of C, its intersection should be non-empty. So here I have taken only two elements of C. So we have already observed that the intersection of these two will be nothing but minus infinity to n, where n is the minimum of n1 and n2, right? So this is the same as this particular example. So it will be minimum of these two numbers will come here in the intersection. So now, since this works, so that means, and then we know that this is a non-empty set, because it contains all the elements n, n minus 1, n minus 2, so on, along with many other points. So this set is non-empty. So therefore, intersection of any two elements of this family is non-empty, and in general, using induction, we can easily prove that this family satisfies uh, so what it satisfies? It satisfies finite intersection property. So here we have seen that so what is this result which we discuss is whenever a topological space is compact, if and only if whenever I have a family of closed sets which satisfies finite intersection property, then the total intersection is non-empty, right? But in this example, we have observed that for R, which is a set of all real numbers, We have considered this particular family C, which satisfies finite intersection property, but its total intersection is 5. So here the condition was total intersection should be not equal to 5, but here it becomes equals to 5. So that is happening because that is happening. So that means this particular conclusion of the theorem is not satisfied. That means X is not compact in this particular example. So using this theorem, we again prove that R is not compact. So C satisfies the finite intersection property. However, in the previous example, we observe that the total intersection of elements of C is null set. Right. So therefore, by the previous theorem, X, which is in this example, X is a real line, is not compact with respect to the standard topology on R. So this is just an example which I wanted to discuss regarding this particular property. So today, next I want to discuss a relevant notion to compactness, that is known as a sequential compact species. So let us see what is the definition of sequential compactness. So topological space X is called sequential compact if every sequence whatever sequence I take in this topological space X, it has it has a convergent subsequence. Right. So if whenever I take a sequence xn, and I can always find its convergent subsequence in X, then the space X is known as sequentially compact space. So usually subsequence we denote by X and K. Right. Let us try to prove a theorem. Uh, so whenever we consider a matrix space means uh, it always contains a metric defined on a set X, so that we usually denote by D, right? So matrix space we usually denote by X comma D, where D is a metric on X. So D is the distance function, and if X is compact, then X is sequentially compact space. So this result we want to prove, and then we will use here the finite intersection property. Uh, Basically, what we proved in this theorem. and this we are going to use here. Okay, so to apply that theorem, we need a particular collection of subsets of X which satisfies the finite intersection property. And what we want to prove is X is sequentially compact. So we need to prove every sequence as a convergent subsequence. So let us start with a particular sequence. So let Xn be a sequence of elements of X. So that means it is a collection of numbers x1, x2, x3, so on. So from this collection, let us consider a collection of sets. So for each natural number n, define an to be the set xn, xn plus 1, xn plus 2, so on. So basically we are in this set we are not taking the first n minus 1 terms of the sequence. We are not taking x1, x2, x3 up to xn minus 1, but we are starting from xn onwards. So En contains all the elements xn, xn plus 1, xn plus 2, so on. So in particular, what will be a5? A5 will be x5, x6, so on, right? And then if we take, for example, a8, then it will be x8, x9, so on. What will be the relation between a5 and a8? So a5 contains x5, x6, x7, but a8 do not contain those elements. So a5 contains more elements than a8. So basically, what we will observe here is that so this sequence a1 will contain a2, a2 will contain a3, and so on. So it is a decreasing sequence of uh, subsets of elements of X, and each of these set contains infinitely many points, right? Because this set contains infinitely many points. So that is very important. And now what I will do is I need a collection of closed subsets of X, right? Because here we consider the collection of closed subsets of X. So what I will do is I will take closure of each an. So an is a closure of an closure is a closure of the set an in X, where X is the metric space. So every metric give open ball. Open ball will give open sets, and once we know open set, we know closed sets. We can define the closure. So an closure means closure with respect to that particular closure coming from the metric. So since a1 is a1 contains a2, c1 closure also contains c1 also. Sorry, since a1 contains a2, a1 closure contains a2 closure contains so on. So therefore c1 contains c2 contains c3, so on, right? Because c1 is a1 closure. So we got now the sequence cn, which is a collection of closed subsets of X, right? Each elements of Cn is a closed subsets of X, and note that if I take any two elements, uh, so if we take any two natural numbers, one is smaller than the other one, m is less than equal to n, then the intersection of Cm and Cn, Cm is Am closure, Cn is An closure, and then we know that Am closure contains Am, An closure contains En, and when we take intersection of Am and En, where m is less than equal to n, this intersection will be An, right? So that we have already observed here that A5 contains A8, so that means A5 intersection A8 is A8. So that we are using here. So, and then we know that each AN is infinite set. So that means in particular it is non-empty set. It contains so many elements. So whenever m is less than equal to n, Cm intersection Cn is non-empty. So any two elements of this family we take, then its intersection is non-empty, and then by induction we can show that uh, any finitely many elements of this collection if I take, then I can easily show that its intersection is also non-empty set. So therefore by mathematical induction, C has we can prove that C has finite intersection property. So now I have a family of closed sets which is finite intersection property. So I can use the uh, this theorem that whenever I have a topological space which is compact, and in which I have a family of closed sets which is finite intersection, then the total intersection is also non-empty, right? So let us use this theorem. So it is given in the hypothesis that X is compact. So from previous theorem, so intersection of the family of the elements of family C is pi. Now what are the elements of C? There are C1, C2, Cn. So that is same as C intersection of Cn is non-empty, right? So now since this is non-empty, we can find a point, at least one point in this intersection. So that is meaning of the set is non-empty. So that there exists a point P in X such that P belongs to intersection of this. And now since P belongs to intersection, P belongs to each Cn, right? And what is Cn? Cn is nothing but closure of An by the definition of Cn. So now I have a point in the closure, and then we know one result that whenever I have a point in the closure of a set, then whatever uh, open set or basic open set I take around the point, it always intersects the set. So so that we discuss when we discuss the closure of a set. So therefore, for each n belongs to n, whatever uh, disk I take around the point P. So let us uh, so let us take for each k. So whenever k is a natural number, I can always find so P belongs to take a closure, and that implies the open ball, whatever ball I take around P, that always intersect AK, right? So this is, we are just using the equivalent condition of the point belongs to closure of set, and so that means every open set or basic open set around this point always intersect this set. And then what is AK? AK is nothing but the set xk, xk plus 1, xk plus 2, so on. So this intersection is non-empty. So now this intersection is non-empty means I will get a number which is in this set k, k plus 1, k plus 2, uh, so that x of that number will be in this set, right? So in other words, there exists a natural number which is greater than or equal to k, such that the corresponding x and k, which is element of this set, is also element of this set. So that means x and k, its distance with the point P is less than 1 upon k. Right? That is meaning of the element x and k is in this set. So the way we chosen this natural number, which is bigger than k because it is element of the set, that gives us a subsequence x and k, right? And that subsequence will goes to 0 because 1 upon k goes to 0 as k tends to infinity, right? So as k tends to infinity, uh, distance of x and k with p, which is less than 1 upon k, which goes to 0. So therefore, since this distance goes to 0, x and k converges to p. So basically we found that the sequence xn has a subsequence xn k which converges to p, and p belongs to x, right? So we started with the sequence xn, and we proved that this particular sequence xn has a convergent subsequence xnk which converges to point p in x. So therefore x is a sequentially compact space. So using this finite intersection property and the characterization of compactness in terms of finite intersection property, prove that every compact space, which is a metric space, is is always a sequentially compact space. So we'll see converge of this result also, but before the converge, we will need a particular lemma which is known as Lebesgue number lemma. So let us see what is the statement of this. So let C be an open cover of a sequentially compact matrix space. So I have topological space XT in which the topology is coming from the metric D, and in which I have a open cover that is a family of open sets whose union is X. Then I can find a positive number that is known as the big number. Uh, then there exists a delta greater than 0 such that for every subset B of X of diameter less than delta, there is an element U in C with B is contained in U. So we want to prove this particular property that whenever I have a compact matrix space and I have a open cover C, then there exists delta greater than 0 such that for every subset V of X whose diameter is less than delta, I can always find element U in this open cover such that V is a subset of U. So let us start proof. I will not be able to complete the proof, but let us start one or two lines, then I will stop. So first we want to find a negation of this statement. So suppose the conclusion does not hold. Yeah, so first of all, let me write down the conclusion first in the mathematical form. So the conclusion is so the conclusion, just 1 minute. Conclusion is that there exists delta greater than 0 such that for all subsets B of X whose diameter is less than delta, there exists element of the open cover such that B is a subset of U. Right, so this is given conclusion of the theorem. So suppose this is false. The conclusion is does not hold. So we assume that conclusion is not true, and then we will find a contradiction. So conclusion does not hold. That means so that is so we want to make a negation of this statement. So that says that for every delta greater than 0, there exists a subset of X so that diameter is less than delta. So that for yeah, so now this is a property. So property fails. So that means there does not exist any element of the open cover such that B is a subset of U. So this is the negation of this statement, and now this is true for every positive number. So now for each natural number, we know that 1 upon n is positive, right? So in particular, if this is true, then if I substitute in particular delta is 1 upon n in this statement, so what we'll get is for 1 upon n greater than 0, there exists a set B, and that depends on n. So I will denote it by Bn. So for every n, I'm getting a set which we will denote by Bn. Such that diameter of this set is less than delta, and for this particular set, there does not exist U in C, such that this is contained in U, right? So this statement is true for every delta. In particular, I am taking delta is 1 upon n, and every delta will give me a set B, so that I am denoting by Bn. Okay, so I think let us close this lecture at this point. So in the next lecture, I will complete proof of this theorem.